Okay, first, several announcements. Reminder: homework 4 is due today at 10 o'clock, and solutions will be posted today at 10:30 so that you can review them before this Wednesday's exam. And the second one is that exam 2 is going to be on Wednesday in this location, Moore 100, from 12 to 1:50. Okay. And this will cover lectures 9, 10, 11, 12, 13, 14. So I think it's the conversion from NFAs to DFAs, properties of some NFAs, and then limitations of regular languages, pumping lemma and others, regular expressions, and introduction to Turing machines. We had 2 lectures on it, what Turing machines are, how to design some Turing machines, and also, last lecture, which was universality and uncomputability. Okay, so just those 6 lectures, and the format will be somewhat similar to exam 1, but given the kind of things that we're studying in the second section of this class, there'll be a bit more emphasis on problems. So there'll be roughly 5 points which are like objective questions, similar to the first 10 points in the first exam, and then 20 points will be problems. In terms of difficulty, the level should be somewhat similar to exam 1. And as I said, my target is for the median to be around 80 to 85% or thereabouts. And yeah, so there are office hours for me from 2 to 3. There are other TAs having office hours as well, so use them if you have any questions about the homeworks and the syllabus, and we'll also be active on EdSTEM to answer any questions about the exam. Okay, and one important clarification, I know this is kind of ambiguous, but I want to allow some room for interpretation here, but not like put some draconian rules. So in terms of writing, when you're asked to write something in the exam to prove something or design a Turing machine, aim for a level of detail that we're kind of doing in class or on the homework solutions. I'll try to be as precise as possible. I also don't want to constrain your thinking too much. Okay, so just remember what kind of the level of detail we're going into in class and what you see on homework assignment, and that should give you an idea of what we're expecting for the exam as well. And also, there are no discussion sections this Friday. Instead, I'll be teaching a lecture from 12 to 2 on Zoom. So please join in for that. We're going to continue a discussion on Turing machines then. And finally, for a few who cannot make it to the physical exam, we will have an online exam at the same time on Gradescope. Okay, that won't apply to most of you here, but for the few who are going to use it, TA and Ray will do the exam. And if you have any questions about the logistics there, again, please reach out to us. All right, any questions about this stuff? Okay, great. Now that we got the dirty stuff out of the way, let's start with today's lecture. So last class, as I said, was one of the greatest hits of, was kind of like the great hits of theoretical computer science. We saw how to represent Turing machines as binary strings, and this led to 2 phenomenal things. One was universality, that there's a Turing machine that can really simulate all Turing machines in the form of being able to compute the eval function. And we also saw the toddler function, which gave us uncomputability, right? There is some function that no Turing machine can compute, okay? And what we'll do today is to kind of push our understanding of computability even further. And it might seem like the toddler function was doing something completely weird, right? What if it's uncomputable? Why would I care about what the machine is doing on its own input? It's something that seems to be defined just so that you break the definition, right? But as we will see, there are many important things that we care about in practice. Like, in systems, these are some of the critical things that have led to many, many bugs, lots of money invested in them, a lot of research invested in them, trying to get around this. And all of them are somehow connected to this uncomputability. Okay? All right, let's get started. And the first example we'll do is the halting problem. So just to recall, we define this function toddler, and roughly speaking, toddler, when given a binary string as input, the output was 1 if okay, if the output of M on itself started with 0, the output of toddler is M and is 0 else. Okay. Just as a funny anecdote, the reason I came up with this function was actually I was teaching this class remote last year, and my daughter, who was actually a toddler then, no matter what I did, everyone could hear her during lecture. So I called it the toddler function. And towards the end of the lecture, end of the course, I told everybody, okay, you're going to meet the toddler. And I introduced them to class, her to the class, and I asked her, do you always say no? And she actually said yes. That wasn't planned at all. Okay. So we're going to use this as kind of the start, the origin for a lot of other stuff we're going to see. The first one was we defined the halting problem. Okay? And remember that these are functions. We are specifying what we want to do. And the theorem that we're going to show today is halt is uncomputable. Okay? There is no Turing machine which can decide whether or not a program is going to halt on an input. Okay? This sounds very nice. I mean, if we could do this, this would be amazingly useful. Right? Imagine every compiler, before you actually execute the code, can tell whether or not this is going to cause a crash. And if so, it will save you a lot of time in terms of running the program and then finding out in the end, after investing all the time and resources to execute the program, that you found out that, okay, it resulted in a crash. It would be great to circumvent that. Right? But unfortunately, we cannot. And how do we show such a thing? So the solution is going to be what we call a reduction. So there's this famous quote, actually I forgot by whom, but it says, every problem in computer science can be solved by one level of indirection. Meaning, you ask me to solve a problem, I'll just kind of point you to solve another problem, right? So we're going to follow something similar here, which is, you asking me to show how whether or not halt is computable, I'm going to reduce it to what we already showed, which is that toddler is uncomputable. Okay? And the way it works is, you want to show the following implication. If halt was uncomputable, then toddler is, sorry, actually, computable. Okay. If you could solve the halting problem, if there is a Turing machine which can compute the halting problem, then there is a Turing machine which can solve the toddler problem, which is a contradiction, right? Because we actually show, starting from first principles, that toddler is not computable. So if we show this implication, then we are done, right? I mean, it's basically a proof by contradiction. It's a little bit like saying, if pigs can whistle, then horses can fly. Okay. And another way to think about it is, think of your reduction as using some kind of library. Someone gave you the magical power to solve the halting problem. Gave you a magical library, which when you call that function from that library, solves the halting problem. And I'm now asking, what can you do with this power? With great power comes great responsibility. And what we're going to do with this great power is to solve the toddler problem. Okay? So imagine we have a box, a black box. We don't know how it works, what it does, but it solves halt. Okay, what can I do with this box? We're going to show that with this box in hand, we can actually solve the toddler problem. Okay? All right. So I'm kind of belaboring this point because we're going to use this extensively, not just for halting, but again and again for other problems. Yeah?
Can you explain why we know they're related? Why do we know that the halting problem, if that's computable, then the toddler problem?
That's exactly what we're going to show. That's our goal. Like, that's essentially the core of the argument. Okay? We are basically showing this implication. We're not really caring about the truth of the two pieces, but just the implication. Okay? All right. So I'm going to call this simulation procedure, which can use the magical box for halting to solve toddler. Just solve Todd using halt. Okay. So what is the goal here? I'm given as input a description of a Turing machine M, and the desired output should be toddler of M. That's what I'm going to do. I'm going to design a Turing machine for this, but we're going to use the black box for halting here. And the way we'll design this machine is really use our have our cake principle. Meaning, I'm going to come up with just some high-level programming description of how this machine is going to work. But that is fine for us. Okay? Just think of coming up with an algorithm which can solve the toddler problem, assuming you have halt. Any suggestions? I think in last class itself, someone pointed out how you might be able to do this if you could decide whether or not the machine halted, right? So recall in toddler, the definition is almost seems like, okay, why shouldn't you be able to do this? I would simulate M on M, and if the final output started with 0, I would flip it. Okay, that sounds like a valid algorithm by itself. But that doesn't suffice to show that toddler is computable. Why? Because when I run M on, when I execute this thing, I might be stuck on an infinite loop. So I never get to check the output and decide what to do. Right? Does it make sense? Like, what's this obstacle in trying to design an algorithm directly for toddler? The problem is we don't know if the input machine M would halt when given the input M, right? But now you have the magic power. You have the box which can answer that question for you. So let's just exploit that. So what should the deduction do? What's an algorithm to solve toddler using halting then? Any suggestions? Yeah?
Say if it doesn't halt, then it just returns.
Right. So let me just say, if I'm going to check whether the machine M halts when M given M as input. So if M halts on M, then I already know, if it doesn't halt, then I already know the answer to toddler. What should I output then? Output 0. Because when M doesn't halt on M, toddler of M is actually 0. Right? On the other hand, if I know that the machine halted on itself, then I can actually run the program to its execution, look at the final output, check the first bit, and then flip it. Right? Okay, so I'm going to simulate M on itself. Actually, there's, yeah, exactly. The suggestion in the chat was kind of the same thing, where once I know whether or not the machine halts, I can use my usual tricks, right? And I need to simulate M on itself, but I can do that because we have a universal Turing machine. I'm going to compute eval of M comma M, which we know is just an algorithm that we can compute, and proceed. Okay, so this is the entire simulation. We just call the black box for halt once. If it says, the machine doesn't halt, then we already know the answer to toddler. We just output 0. If it says you halt, then we're just going to run through the simulation. We're going to run eval of M comma M using a universal Turing machine. So you are using the universality result strongly here. And then you just check the output. If the first bit of the output is 0, then the output should be 1. If the first bit of the output is 1, you have to output 0. That's it. Okay? Any questions about this? Yeah?
Why are you setting the halt and 0 to be basically output 0? Why is it?
So if so basically in the definition of toddler, if the machine doesn't halt, then the output of the function is 0. Right? So if M comma M halts and starts with the 0, then we output 1. In all other cases, we just output 0. So in particular, when it doesn't halt, you have to output 0. The definition says the answer is 0 in that case. Okay? Any other questions? It's a question, shouldn't the arguments to halt be M comma the bit string of M? Yeah, that is true. So we mark M above really means the binary description of M, right? Because the way we define halt, it's taking binary strings as input, right? So when I write M comma M, it should be appropriately encoded as a binary representation of the machine M. Okay? But that's fine because the encoding doesn't matter. I'm just hiding that here. So this entire simulation implies that if halt is computable, then Todd is computable. Okay, but we already know that Todd is not computable, so we get a contradiction. Therefore, halt is uncomputable. Okay. Any questions about this? All right. So let's maybe understand this a little, right? So we showed the halting is uncomputable, but let me ask you, is halt really hard? What do I mean by this, right? So somehow, when you look at this reduction, it seems like halting is only hard when I give it some weird, like a Turing machine running on itself as input, right? It seems like the problem is hard, but once again, some sort of pathological cases, right? But that's only an appearance. It is genuinely a hard problem. Okay. One way to think about this is that there are many questions in number theory, for instance, which can just be boiled down to a simple short program being halting or not. Okay. I can give you the text of some 10 lines of a program, and if you can tell me whether or not this 10-line program halts, then you'd have solved like a many centuries old conjecture in mathematics. That's just an example that halting can really be a hard problem even for very short programs. It has nothing to do with the length of the program. Okay, so let's do an example just to illustrate this point. How many of you know the Goldbach conjecture? Maybe you heard of it. What does it say? Well, it's almost like 500, 600 years old. It says that every even number can be written as sum of two primes. Okay? Every even number can be written as a sum of two primes. That's it. We don't know whether this is true or not. Okay? But why am I talking about this here? Well, consider the following simple program. I'm going to call it def Goldbach Z. Okay? I'm going to say n equals 4 while true So, and what I'm trying to illustrate is that here's a short program, okay, about 10 lines. The program halts only if Goldbach conjecture is false. Okay, so for P in range 2 comma n minus 1, if E is prime Okay, so I'm just checking whether or not I can write this number n as a sum of two primes by kind of enumerating or all possible ways. You know, for every number in the range 2 comma n minus 1, check if p is a prime and whether n minus p is a prime. That is, I've written n as sum of two primes, right? And here, let me just put this dash. If you succeeded for this n, I'm going to write n equals n plus 2. That's it. Else, break. This break is for the outer while loop. Okay? So there's a question in the chat. I'll get to that in a second, but let me finish this thought. So this is a pretty simple program, right? And halt of this program, let me call it G, is zero if Goldbach conjecture false, one else. Okay? So even for very short programs, deciding halting is extremely non-trivial. Like we don't have an answer to this question. You might have thought that maybe if I limit the size of the inputs to the halting problem, that I'm only interested in short programs, I could maybe do some tricks to check whether or not the program halts, but not really. Okay? And you can do similar stuff for, like, let's say even Fermat's last theorem. I can write down 10 lines of code. It's even simpler here. You don't have to even have primes and so on. And the program would halt if and only if Fermat's last theorem were false. Okay? So you can do all kinds of weird stuff like that. The problem with halting is that programs can be insanely complicated even though they're very short. Okay? That's what you should keep in mind. Is halting problem really hard? Yes. Even for very short programs, programs can be doing extremely non-trivial things, so we won't be able to tell them apart. To tell whether or not they halt. Okay, and now let's go back to this question here. The question was, why does this new program imply halt is computable? Wouldn't it only imply that we can determine if Todd halts or not? Not necessarily that Todd is computable. So if you go back to this logic here, what it's saying is if we had an algorithm for halt, I would just plug that in as a black box, and the entire thing would be some Python program for computing toddler of m, okay, which would violate our theorem from last class. Okay, so we are actually not just checking whether the machine is halting, we are also computing the actual output of toddler. When the machine m doesn't halt on m, we are matching the functionality of Todd exactly, right? And the same for other cases. That's why we are being able to compute Todd here. Okay? Any questions? Okay. So let me say that this program is really a binary string of maybe a few hundred bits. Okay, that's it. So if I could solve halting on programs which are only a few hundred bits long, then magically I would have solved many number theory questions and all kinds of other stuff. But we don't believe we can do that, even for such short programs. Okay? Yeah?
So if we say that a halting problem is uncomputable, does that mean that there is no way to figure out if the program will halt? Or does that just mean that there is no algorithm to figure out if the program
Yeah, so it depends really on, I mean, we really think that being able to figure out is to have an algorithm. It definitely means, by definite, like, by what we showed, that there is no algorithm to do it. Okay. And like, it's not, that means that you should not really be able to tell them apart, whether or not the program halts. Like, it's not like, maybe I can come with a quantum computer, that's not going to happen too. Okay. Any other questions? Yeah? So that's just a convention for us, right? So eval of m comma m, imagine I actually have a compiler which is just running a program which is just an infinite loop, right? And if I don't put a time limit, it's just going to keep on going forever, right? And the perp is not really the output sign, it's just our convention that the machine did not terminate. Okay? It's not the output of the machine, it's just our notational way of saying, okay, the machine is still running. All right? Okay, so let's now okay. Actually, that's a good question. Shouldn't halt take 2 inputs? Let me say 0 here. It doesn't really matter, right? I can, in this program, we can just give any input, and I did have a typo here. The machine halts if the conjecture is false and doesn't halt if the conjecture is true. It's a good point. Thanks. Okay. So what we did here is essentially a reduction. We showed how to reduce solving thought to solving halt. Okay. So let's formalize this process. Okay, so what we saw so far was that halt is uncomputable and thought is uncomputable. Okay. And starting with these two as the base problems, we can build a whole web of connections showing that various kinds of problems are also unsolvable. And we'll do this through the language of reductions. Okay. And what do reductions really do? They're a way to transform one problem's input into another. So basically, you use it in the way saying, if I can solve F, solve a problem, then I can solve another. Okay. So more concretely, what we are going to talk about is the following. So we will say reduce problem A to problem B. Okay, so what does this mean? Intuitively, what this means is that if I can solve problem B, then I can solve problem A. Okay. So in other words, if someone gave me a magical box to solve problem B, then I can use it to solve problem A, right? And sometimes, you also talk about this by saying this is equivalent to saying reduction from problem A to problem B, right? And the reduction essentially, and this is important, reduction is essentially an algorithm that translates inputs for one problem to inputs for another problem. Okay, so we'll talk about what this means precisely, in a few minutes, and then I'll give you specific examples to illustrate their power. So what is the formal definition? So let's say we are reducing from F from G to F. Okay, so suppose I have some function G, and I have another function F. Okay, so what we are trying to say is that we are reducing from G to F, meaning if I can solve F, I can solve G. All right, and the way we will do it is the following. So the reduction will have three parts. There is a mechanical way to think about this, and this is the mechanical way. We can think of the reduction as having three parts, each of which is very important. So the first one is specification. Or, in other words, what? So what we are looking for here is to tell you what the reduction should do. So the reduction is a function which, as I said, which transforms inputs for one problem to inputs for other. So here it should really be inputs for G to inputs for F. Okay. And the main identity we want here is that G of X on any input X, the output of the function G is the same as the output of the function F on R of X. Okay, so this is the most important property that the reduction must satisfy. Okay. And intuitively, the point of having this property is that if somehow somebody gave me a black box for F, and I'm looking to solve G, then I take my input for the problem G, which is X, run it through my reduction, which now generates an instance, an input for the other problem F, and I use my magic box on this new instance that I generated. Okay, and the specification is what it is, but we also need to make sure that this specific reduction is not where all the complexity is hiding. Okay, so we want implementation as well. Or how? We need to make sure that the reduction itself is computable. So we need R to be computable. Okay. And finally, we need to also show that the analysis actually, that their construction works. And this is the third step. So analysis or why. Okay. I mean, you came up with some reduction, but we need to argue that it actually works. What does it mean for it to work? We need to show that the star property, which is what allows us to compute the function g using f, holds. So we need to show that star holds. Okay. In particular, we need to show that for all x, g of x equals f of x. F of r of x, not f of x, but f of r of x. Okay, so pictorially, what we are doing really is the following. Somehow you have the space of inputs for g, and then you have the space of inputs for f. They could be living in completely different worlds. You know, maybe g views its inputs binary strings as programs, f views its inputs as strings, you know, maybe as a graph or whatever we have, right? But the reduction goes from one space to the other. It takes an input for g and maps it to specific input for f. Okay, and the power it allows us is the following. So suppose we have a reduction R from G to F, okay, just as above. Okay, meaning if you give me a black box for F, I can solve G. So in other words, if F is computable, then G is computable. Okay, if I have an algorithm for F, I can just use my reduction, which itself is a computable transformation, and run the algorithm for F on this transformed input to get the output of G. Okay, and now the contrapositive of this, which is where we are going to use it most often, is that if G is uncomputable, then F is uncomputable. Okay, so the real power of the notion comes from this contrapositive. Okay, I mean, that's a lot of terminology, but let's see an example to illustrate these points, right? So just now we saw that the halting problem is uncomputable, and we will use that as a starting point to show another problem that seems related to halting, but could potentially be much easier is also uncomputable. So let's see an example of reduction. Okay, so let me define a function which is the following. Let me make a bigger box. Halt on 0. Okay, it takes a binary string as input and outputs a 0 or 1 value, and is going to view the binary string as the description of a Turing machine and do the following. The output is 1. Okay, this could be confused with the perpendicular symbol. So is 1 if M, the input string when viewed as a Turing machine, halts on 0, meaning halts on input 0. Okay, and is 0 else. Right, so you take your machine M, run it on the input being just the string 0, and then check whether or not that halts. So this is different from halt, right? You know, the halt problem takes a specific input, but here you're only interested in the behavior of halt on 0. Okay, so as a remark, halt on 0 only depends on behavior on M, behavior of M when input is 0. Okay, and as was asked actually in class, halt of M comma X, I cannot just, you know, ignore the input X and run halt on 0 on M. Okay, such an equality need not be true, because, you know, maybe the machine M halts on the input 0, but it doesn't halt on the specific input X. Okay, so they can genuinely be different functions. I mean, the inputs are different, but, you know, you can't just encode one into the other like that. All right, so the main claim that we are going to show is the following. Halt on 0 is uncomputable. Okay, not only is halt uncomputable, I mean, halt does seem harder, right? Because you have to check whether or not, I mean, halt on 0 somehow seems like you're only interested in the specific input. Whereas halt, there was also the point that you're only interested in running M on X. Okay, and the way we will prove this is to reduce from halt to halt on 0. Okay, so what does this mean? We want a reduction which takes inputs for halt, right, and then maps it to inputs for halt on 0. Okay, so that's what we want. And if we do this, then we would gain some information about the power of halt on 0 as compared to halt. So let's try and see what we can do. Okay, and what should the reduction be? So remember, reduction is just a way to map one input space to the input space of the other. And the inputs for halt are a program M and then in like specific bit string X, which we're going to run the program M on, right? Program Turing machine, I'm using them interchangeably because our cake principle, right? And for halt on 0, the input is just some other program. Okay. So what we're going to do now is, suppose I had the description for M and X, I'm going to write down description of a new program. And the new program is defined as follows: R of M of X, okay, is the following program. Okay, so it just says return eval M comma X. Okay, and that's the definition, that's the specification. And the first thing to check is, we kind of got the what, but also let's see how, right? So what is as defined above, right? So how we need to argue that R is computable. Okay, and we're just going to use our cake principle here, meaning it just suffices to show that R can actually be written up, can be computed in some programming language. But what does it mean to say R is computable here, right? We are not going to run eval of M comma X. We are just going to write down the description of the program which asks you to do that. Okay, it's just processing one text file, which is the description of M, to another text file which corresponds to this program. It is not executing M on X. That is very important, even though it's a little confusing. Okay, so R just writes down the program and as a binary string. Okay, and we can, R is computable by have our cake principle. Okay, what do I mean by this? So we have a high level description of what R is supposed to do. Okay, it takes the text file corresponding to M and spits out the text file for M, but it is not running M on X. It's just writing down the instruction. Okay, the first command is run this program on X. That's it. But it is just the program description is that. Okay. So now we kind of have the what and how. We need to do why. Why is this a valid reduction? Why does this even make sense to look at this? So the why typically also has two steps. So what do we mean by two steps? So we need to show the following, right? Recall the star equation. Y corresponds to showing that for all inputs, halt equals halt on 0 of R of the input. Okay, so we need to show that halt of M comma X equals halt on 0 of the reduction applied to M comma X, right? So recall we needed G of input equals F of R. Okay. So let's check this. We need to check an equality here, and we can do this in 2 steps. Case 1, halt of m comma x equals 1. That is, m halts on x. Okay. So remember, halt is a function. It takes a program and a specific string x as input, but it's a function. We're saying the function is 1, meaning m halts on x. What happens when m halts on x? When I run n, that corresponding program is going to halt on all possible inputs, because n just completely ignores its own input and runs m on x. So its behavior is kind of oblivious to its own input, but it only depends on what's happening here. So implies n halts on 0. In fact, n halts on all inputs. Okay, so if you think of n as now a program, it's a program which will halt on 0. So i.e. halt on 0 of n equals 1 as well. Okay. So the other thing is, let's do case 2. I mean, we kind of showed what happens when the function evaluates to 1, but to show equality, we have to consider both cases. Okay. What happens if halt on of m comma x is 0? That is, m does not halt on x. Well, what happens here if you go back to this program? The function n, the program n now, would not halt on any inputs, right? It's completely ignoring its own input and just running m. So the program n would not halt on any inputs. So implies n does not halt on 0. So therefore, halt on 0 of n equals 0. Okay. So that means we have the equality as desired. So we just showed a reduction, right? We have all the 3 ingredients, the what, how, and why, from halt to halt on 0. Therefore, we have a reduction from halt to halt on 0. Okay. And what does this imply for us? It would imply that if halt on 0 is computable, then halt is computable. Okay, so we can use the black box for halt on 0 to solve halt, but we just showed that halt is uncomputable. So this together with halt is uncomputable implies that halt on 0 is uncomputable. Okay. All right. So that's, a way to show that new problems are uncomputable from old problems. Okay. So let me do one more example. Okay. So summary starting. So we show reduce, we have a reduction from halt to halt on 0. Okay, so that's exactly what we did. And now let's do one more example. Okay, and this example is the following. The function might seem a little silly, but it's a good illustration for these reductions. And the function is what I'm going to call not empty. It takes a binary string as input and outputs a bit. And we're going to assume that the binary string actually is a Turing machine. So we'll interpret that as a program. And essentially, we want to check whether or not there is some input which would make the program accept, meaning the program would end up outputting 1. So not empty of m is 1 if there exists a x such that m of x equals 1 and is 0 else. Okay, so that's the definition. If there is some input x which can make my program m accept, meaning output 1, then not empty of m is 1. Otherwise, for no input, m of x evaluates to 1, then not empty of m is 0. Okay. Now the theorem that we're going to show is that not empty as a function is uncomputable. Okay. And the way we will show it is to do the following. If I can solve not empty, then I can solve some other hard problem. Now we're trying to show that not empty is a hard problem that no computer can solve. And the way we'll do it is to say that, suppose somebody gave me the power to solve not empty, then I can do something even more amazing or seemingly more amazing, which is, for example, then I can solve, let's say, halt on 0. Okay. You could show it for a halt on 0. Any one of those would be enough to show not empty is uncomputable. Again, by contrapositive, right? We just argued that halt on 0 is uncomputable. But if you can solve not empty, if not empty is computable, then halt on 0 is computable. So you get a contradiction. Okay. And we are going to do that again by a reduction. So remember, we want an algorithmic transformation which takes inputs for one problem into inputs for the other. In this case, we are reducing from halt on 0 to not empty, right? So meaning I need a way to translate inputs for halt on 0, inputs for halt on 0 to inputs for not empty. Okay. And so here the inputs for halt on 0 are programs. M and here are also programs. So we need to go from one notion of programs to the other. Okay. And we want this conversion to satisfy the property that for any input string m, when we view it as a program, M halts on 0 if and only if the corresponding program that the reduction outputs has a string which makes it output 1. Okay, so that's the property that we want. So meaning, if you think of M as some sequence of lines, def, whatever, right? You have some lines here, that's your M. Then we want to translate it to some other program. And maybe it's def, you do all kinds of stuff, but that's the program. That's the text file that you're going to run not empty on. Okay. So you're manipulating programs and passing them as input to not empty, which is a function. And what should this reduction be? Well, let's think about it, right? We need a way to encode whether or not the program M halts on 0 into another program whose behavior, whether whether X has, whether the new program has an assignment or has an input which makes it output 1. Okay, so let's do the following for that. So it requires some practice and maybe some ingenuity, but at the end, most of the reductions that we are going to look at are essentially going to be somewhat simple, but they're simple when you do them right, or kind of when you look at them. So here's my new program, which is going to look at any possible input. Okay, let me even just use X here. Completely ignores its own input, but then runs M on 0. Okay, and then says return 1. Okay, and remember, when I say runs M on 0, we're not really executing it. It writes on the code, the instructions corresponding to this. So no one is executing M on 0 here. I'm just writing down a program with these instructions in it. Okay. So there's the subtle confusing difference that even though it says run eval of M comma 0, we are never executing M on 0. We're just writing down the program which corresponds to this set of instructions. Okay. So this is the what. So we described what the reduction is doing, how it's transforming inputs from one space to inputs for the other space. Okay, and how? Why is R computable? Well, by HOC, right? We just have to add a few lines. Okay, and we know eval is computable. Okay, so there is a small program which we can use to, there is a succinct program or universal Turing machine which can compute eval. So somehow that's what allows us to make sure that R is computable. In essence, if you think about it, the reduction R of M, the output is going to be the program corresponding to the instructions for eval followed by return 1. That's it. Okay. So we are using the universality in a strong way here. And now let's check the why. So why, meaning we need to check why, whether or not this condition, which is at the heart of a reduction, holds. So checking this condition always comes down to like case analysis, most of the time. So case 1 is halt on 0 of M equals 1. Okay. Or let's say, let's start with the case where it's 0. That is, M does not halt on 0. So what happens in this case, right? If M does not halt on 0, what does this say about the behavior of the program corresponding to R of M? So the program R of M would always just be in an infinite loop now too. It would always on any input would not terminate just because you're trying to execute this first step. So you never get to the second step. So on all inputs, the new program N is not halting. In particular, there is no input to make this new program N output 1. So what does this mean? So that means that not empty of the new program is 0 on all inputs to N. We are not halting. Okay, I mean, whether or not you're not halting, that's not important, but what's important is that you're not able to get to the second statement, which is telling you to output 1, right? And that's the main thing. Now let's see what happens in the other case. Halt on 0 of M equals 1, right? So that is M does halt on 0. Well, what happens in this case, if you go to the new program N, on any input X, you would terminate in the first step, and then you'd go to the second step, which is returning 1. So on any input, the output is 1. In particular, there is some input to N, which makes it output 1, right? So in this case, we have not empty of N equals 1. So on all inputs to N, we output 1. So in particular, there exists 1. It's kind of a silly way to saying there is at least one input on which N outputs 1. Okay, so we have this equality now. Okay, that for all things on halt on 0, this behavior is exactly captured by the behavior of not empty on the transformed input. So what does this buy us? It tells us that, so we have a reduction from halt on 0 to not empty, right? So in particular, what did we just show? We showed that if I can solve not empty, then I can solve halt on 0. Okay, if I can solve not empty, then I can solve halt on 0. So, but on the other hand, just a few minutes ago, we showed that halt on 0 is uncomputable. But this is so when combined with the statement that halt on 0 is uncomputable, we'd get that not empty is uncomputable. Okay, so that's how reductions come into play. You reduce one problem to the other, meaning if I can solve a problem, then I can solve another problem. And then you use this implication either in the contrapositive way. Okay, so let's summarize a little bit. So in summary, suppose I want to show that F goal is to show F is uncomputable. Okay, I'm trying to show that some problem, like let's say not empty, is uncomputable. Then what you show is the following. If I can solve F, then I can solve some uncomputable problem. Some problem that we know is uncomputable. Some problem that we know is uncomputable. Okay, so that's the way, I give you some problem F and I ask you to show it's uncomputable, or you're interested in figuring out, oh, is there a computer, is there an algorithm to solve this problem? If you suspect that's not the case, then the way you'd approach it is to reduce an already known uncomputable problem to the new question that you're looking at. If that seems confusing, basically think of it as a black box. If I have a black box for F, then I can do something that I shouldn't be able to. So the black box does not exist. Okay. So that's the main way to use reductions. And remember, the reductions have three parts. You have to first tell what the reduction is doing. How am I transforming inputs of one problem to the inputs of the other? Then how the reduction itself, the transformation should be computable. There should be some automatic way to convert inputs from one to the other. And the third part is why. So often maybe it really goes to, it can be simple or complicated depending on how well you define or how you define the reduction. So you have to show that the equality that is the heart of the reduction holds. And you do it typically by two cases. First, check what happens when the output of the function is one thing and then the other. Okay. So we will use this to the extreme in a little bit, especially in the next lecture. But there's one thing that we should observe about all the things that we're showing to be uncomputable so far. So there are all kinds of talking about properties of programs, right? You view your input string as a program, and then I'm trying to decipher something or some behavior properties of the program. Toddler was something weird, like, whether the program itself would accept, what happens when I run the program itself as input. Halt on 0, what happens to this program on an input string X. And halt was, halt was what happens when I run this program on input X. Halt on 0, what happens when I look at the program? Does it halt or not on the input 0? Not empty. Is there any input which makes my program output 1? Okay, so all of these are somewhat talking about properties of programs. And the extreme version of this is software verification. Okay, so what do I mean? Suppose someone gave me two programs. Okay, and told me that these two are equivalent. The main question then for many important things in practice is this automatable. Is there an automatic way to check, to verify that program A's behavior is the same as program B's behavior? So for instance, suppose I gave you this program. Okay, let me call it double and it says if n is less than 0, return 0, else return 2 times n. Okay, that's a program. And I give you another program, which is double 2. It starts out the same. If n is less than 0, return 0. Else, okay, we don't need else here really. So let's say I start with I equals 0, and then for j in range n to I to I plus 2. Okay, and finally you return I. Okay, we as humans, when we see these text lines, know that the two programs are equivalent. They have the exact same behavior on all possible inputs when the inputs are integers. But can there be a systematic way? Is there an automated way to check this? Imagine, along with compiler, I want to come up with a program which takes these two text files, these two strings as input, and tells me whether or not their behavior is exactly the same. Okay, again, it's like a meta question, but this is something that would be deeply impactful, right? So for instance, imagine you have programming assignment. Instead of giving a bunch of test cases to check whether or not your solution is correct, I can just check for equivalence. Is your program the same as the one that I wrote up and I know is correct? Okay, so that's one kind of way, but software verification has many other applications. Alas, as we'll see in the next lecture, software verification is actually impossible to solve. There is no way to automatize this verification process, and many other things that we'd like to solve turn out to be unsolvable, especially when we're interested in meta questions about the programs. Okay, so we'll talk about that in the next lecture, which is on Friday. And on Wednesday, we will, of course, have the exam. See you then.